Welcome to this exercise session where we will be solving another rotating thin disk problem. This time, I will use Python as a tool to help me solve some of the mathematics of the problem and also tackle two tasks at the same time. They are solving the problem and creating the report. So let's take a look at the description of the problem. It says here, so I have here my Python environment. It says that a steel rotor disk is part of a turbine assembly and has an uniform thickness of 40 millimeters. So this part here where I have the cursor of the mouse here, so this is 40 millimeters. And the disk has an outer diameter of 600 millimeters. So from the center to this part, kind of written as RO, this is 600. Well, completed 600 millimeters, so this would be 300 millimeters. And a central hole of 100 millimeters. So this is 100 millimeters, so this is 50 millimeters. If there are 200 blades, each of mass 0.0153 kilograms, so this is the rotor, and these are the blades. I just tried to draw those blades, two of them. So they are positioned something like this, I would imagine. And they said that they are pitched evenly around the periphery of the disk and has an effective radius of 320 millimeters. So this is the effective radius. It's a measurement of the positioning of the blades. So these 200 blades are going to be equally or evenly spaced around the periphery of the disk here. It says determine the rotational speed at which yielding of the disk first occurs according to the maximum stress criterion of elastic failure. We're talking about Tresca in this case. We have another case. So we're asked to determine this omega or W. Well, it's different, but for steel, we have the Young's modulus, we have Poisson's ratio here, we have density of the steel we're using, and also if we are going to use a maximum stress criterion, it means that we need to compare that to something, and in this case is the strength of the material of the rotor, which is this 500 meganewtons per square meter. So those are 500 or 500 million pascals, something like that, yeah. Great, so what I have here is the libraries I'm going to use. Actually, I'm not going to use these 3-layer libraries. So I'm going to use just these ones. Yeah. And these are the formulas we're going to be using. So the only difference with respect to the previous exercise is that I'm not using the right away solved equations, but I'm using the general equations that will allow me to then not customize, but take the particular conditions of the problem and adapt my equations for the radial stress and circumferential stress. And also there is another equation appearing here with respect to, or different from the previous exercise, is that the centrifugal force. And the reason for that is that this is going to be very influential in the way we handle the boundary conditions to solve for C1 and C2. So this is very important, and you'll see later. So okay, we have the equations, and then what I'm doing here is that let me Alt-Z to just show everything kind of within the screen size width. And these are all the symbolic variables because I'm going to be solving things and modifying, moving things around. So I prefer to work with symbolic variables. So I have the option later to substitute what I need to substitute. That's perfect. So these are the symbolic variables I'm going to be using. Later, I might be using another one that I would include later, but this is basically, I have the mass, angular velocity, mass of the blade, and number of blades, effective ratio, or effective radius. We have the thickness, our diameter, internal diameter. This number of blades, this is repeated. I don't need it, and I don't need this one here. Why these are two of these? Well, this is strange. So I don't need from RF. I don't need not even these two, and I don't need these two because whatever you write on the left side have to appear on the right side here. So I have the IE, nu, rho, sigma, y, and then all of these. Perfect. I think they're correct. Let me see. Yes. And then what I have written here are the known values. So I have the thickness value is 0.04. Well, I could say just 40 divided by 1,000. And that's in meters. And then the outer radius value, inner radius value, a number of blades, mass of each blade, effective radius value here. I have the Young modulus. Again, I have converted them all into basic units so I can work freely without worrying about unit conversion later on the road. So I have a Poisson's ratio that it doesn't have any dimension, it's dimensionless, the density of the material, and the strength of the material we're going to be using. Perfect. So by using this, I guarantee that again, I don't need to change any units in between, in the solution of the problem. So everything is set up for all of this. And the other thing that I have done here, let me run this, is that I have written the equations in symbolic form. So I already have it ready to start working with them. So I'm going to execute this. Let me see. And then these equations that I'm presenting here are exactly the same as these equations presented here. The only difference, let me see. Yeah, the only difference is that the 1/2 is substituted by 0.5, and 1/8 is substituted by this number here, 1.025, represented, well, seeing these ones here. So this is already computed. Let's put it in that way. So let me do a final verification. The radial stress is 3 plus nu. Radial stress is 3 plus nu. Yeah, nu. Yeah, I have it here. Perfect. So one nice step we could do here is to substitute the known values, those values that we know they're not going to change in the problem. For example, the density, nu. I know that those values are not going to change, so I could substitute those values in these equations right away. So let me write a comment here. Substituting known values in the radial. Let's go. Just going to take some and circumferential equations. So I'm going to execute this out. So I have a comment because this is what we're doing right now. And then I'm going to write here. So let's see if Copilot can help me. Known value to equations. Perfect. Let's see. Well, yes. So it's something like this, but not exactly. So because I need to put that sigma r equation, it's going to be, I'm going to take the same sigma r equation and I'm going to substitute something in there. And then I'm going to put it like this first. So I know that rho, the density equals to rho value. And I know that, again, omega I don't know, but I do know nu is equal to nu value. Perfect. And then I can close this and close this. Let me see what is missing here. What is the error I'm having here? This one. It looks correct. So I can display this equation. Here, let me substitute the other one, sigma theta equation, and then does the same. Just, I don't know why it's giving me that warning or message, but it should be the same. Yeah, well, there was something missing there. Yes, and then I'm going to display them. Yes, I'm going to display them like that. Perfect. So let's see how, after substituting in here the equation, the values for rho and nu, how these end up, or how is the shape of these equations. Excellent. This is what we have now. Perfect. Now, having these equations in function of the integration constants, the radius, and basically the angular velocity, which is the unknown that we have been asked to find for a certain condition, then we need to start applying what are the boundary conditions in here. So we're going to have two boundary conditions to solve for C1 and C2. And let's apply the first one. So the first one, let me write down here, applying boundary conditions. So the first one is going to be that when, let me write in terms of a formula, so it's better. So when r equals to the outer radius, this one here, then what's going to happen is that the radial stress, this is LaTeX way of writing formulas, is going to be equal to, no, it's not going to be equal to 0, as in some cases we've seen, but in this case, we are going to have something in the outer radius in here, pulling outwards kind of the whole disk. So in the whole periphery of the disk, we have the blades. Those blades have a mass. So that mass, due to the rotation of the disk, so they're going to exert a centrifugal force outside, so outwards in the upward direction, and that force applied in this rim area, so in the periphery of the disk, is going to create stress. So we're going to have a stress in there. So let me go back here. So the sigma is not going to be 0, but it's going to be equal to this, a stress created by the centrifugal force that is created by the mass of the blades, something like this. Yeah. And then let me comment back here. So how much is that stress created by the mass of the blades? So the stress created by the mass of the blades is, well, equal to what? Now let's write it. Well, we can write it here. So it's going to be that sigma z, see here, it's going to be equal to then the rate, kind of dividing the centrifugal force by the area of the rim. And I'm just going to use area there because this is the only area we're going to be using. Then I'm going to execute this area here, let's say, this cell, and I have this equation. Perfect. So the first thing I need to do is to find out, just check if I wrote this correctly. This is not 0, this should be O, yeah. Is how much is the value of the centrifugal force, how much is the value of the area, and then how much is the value of the stress created by the centrifugal force. So let's do it in that order. So let's say finding the centrifugal force. So actually I could add here in this cell, just for the report purposes, first we will find the expression for the centrifugal force. There we go. And we're going to have a nice report later, after this. So then what I need to do is take the value of the equation of the centrifugal force, this one here, and substitute what I know about things. For example, where is that centrifugal force being formed, and meaning which radius should I use for that, and then what's the mass that I need to use. Okay, so let's see. So first I need to find out I know that the centrifugal force, I'm going to write down here, depends on what? Depends on the mass, depends on the angular velocity, and depends on the radius. Yeah, but I only know the mass, and I know the radius where that centrifugal force is being developed or created. So I know that the mass is going to be equal to this, and let me put it as a, this is amazing. So the mass of the mass value, actually, let's put mass value. Yeah, the mass value is equal to the mass of the blade times the number of blades. We know that, but this has to be value, and this has to be value. Yeah. And then I know that the radius I need to use for this case equals to the effective radius value, because those are the numeric values I'm using. Yes. Actually, let's call this R value. This R value is going to be changing. Actually, I can put this as a comment because I don't want to repeat the equation. So now I can substitute the equation. Look at this. Look at this. So I have the mass. I don't want to substitute the omega. I don't want to substitute the mass by the mass value. I want to substitute the radius by the effective radius. So perfect. Now, after calculating this, I want to display this equation. Look at this. And as I know, this is going to come with a lot of decimals, so I'm going to restrict the decimals to 3 decimals only. There it is. And let me just cut this one, and let's execute this. So we found the mass of the total number of blades, and then we substituted the mass and where that force was developed. So in the radius equal to this. So let's see how it goes. Perfect. So it means that the centrifugal force depends on the square of the angular velocity. So as we know, so for this condition, so one increasing step on the value of the angular velocity, so we'll increase tremendously the centrifugal force in there. Okay, perfect. Now let's find the area. Let's find now the area of the rim. Yeah, we will use A2. All these are not this area. Perfect. Now we have here, let's see what we have. So the area, as mentioned, is this area of the periphery of this. So it's going to be the radius, the outer radius, times pi. Yes, and then it's going to be multiplied times t to find that area there. Or well, is basically 2 pi times the radius times the thickness. So let's write it down here. Let's see then. So expression for the area of the rim. So that is area. Should I leave it like this? I think so. Let's see, I'm going to use 2 times symbolic pi. Yes, that's just to keep it consistent. Times, yes, times, what else? The radial, yeah, the radial, r, yeah. Now I don't want to substitute anything like this. So let's see, it's 2 times pi times, let's change the order here, so I have t. Perfect. And then I could having this, let's see. So I know where the r is going to be formed, I know the t, so I could say, sure, that area value equals to, substituting the radius where is the outer radius, and then the t value, yes, that is, and then we can just display, so to show how much is our result. Let's see. It didn't substitute it. Yeah, maybe it doesn't want to. No, this one here. Yes. Yeah. We can force, for example, we do it, I think. No, I didn't want to do it. Well, it's okay for us. So we can keep it like that. So this is the area. Perfect. Now having the area, let's calculate, or let's form this expression for the stress caused by the centrifugal force. And let's add this code here in the bottom is just to style a little bit the letter here. So if I run this, so it changes to another type of font, and that's it. So let's add the code there, and it's going to say, well, now, it's a forming or expression, just comment in the code, expression for the stress due to the centrifugal force, and then we're going to call yes, that is correct. And again, let me see how this comes. Let me display this equation. Yes, this is what I like. Look at this. Look at this. This is perfect. It's too bad that I didn't want to substitute these equations here, but that's okay. We will do it now later. Now, I could just try to do it here, sigma c value. Let's put sigma c, yeah. So I want to substitute the radius in this equation, which happens to be the effective radius. Let me see something here. No, this is not. I'm just trusting too much. But let me see. So if it's giving me this a value, sorry about this, that just happens. Just want to. No, I don't want this. Let me see how it goes. Wow. Divided by p. So that should be something. If I wanted to just get rid of this, because I'm using the symbolic pi. So what about if I try just to use the regular pi and then use this, and then that's better. Then let's limit the number of decimals here to 3, and there we go. Now we got the expression for the centrifugal force. Awesome. Now that I have this, now we can properly form our first boundary condition. Okay, let's go now writing the expression for the first boundary condition. So we're going to have that is going to give me what? Well, I'm going to call it sigma. We said that when r equal r, the outer radius, then we were going to have that sigma r equal to sigma c. I'm not writing this again because I already have defined that boundary condition in here. So it's already written for my report if I wanted to. But we'll call this sigma r1. So this is the first expression. And then what I'm going to do is that, yes, I'm going to substitute the value of sigma r equation, which is, yes, this one. Yeah, I'm going to substitute the value of the, the value of the radius in here. But also, let me see what this gives me. Let me see. Nice, but again, let me restrict this to 3 decimals. This is the annoying part, but it is worth it. So here we have it. Perfect. But now this is not what I wanted, because I want the boundary condition equation, and that boundary condition equation, I'm going to call it again sigma r1, like boundary condition 1 equation, and this is going to be an equation. I'm going to form an equation that's going to be, yes, that this one here equals to sigma c. And when I kind of, let's say, yes, print out this one here, so just this one, I'm going to have the equation resulting from applying my first boundary condition. Now, let's work with the second boundary condition, and that's going to happen, just go back in here in the disk. So when we are focusing on the internal, say, surface or perimetry of this, so we know that at r equal to r1, ri, internal radius, the radial stress is going to be 0 in that part. So that's our second boundary condition. Let's write it out in here. So in the end, so we have transited all of this, and then our, let's say, second boundary condition happen at, and I want to write like formula r equal to ri. Yes, then I'm going to say that at that point, not about point or surface, that region, then we're going to have that the radial stress, sigma r, equals 0. There it is. Now let's build the expression for this boundary condition. Perfect. So let's write some code here, and then let me put the comment. So comment for the coding part is that second boundary condition. Yeah, r equal to, yeah, no, it's not r, it's 0. Yeah, we put 2 points here. Perfect. So let's write it up. So we're going to call that, we call the other one, let me see here, this is the part I need to focus, so let's keep consistent, sigma r2 for the second boundary condition. Yes, so it's going to be when r equals the internal radius of the disk, of the hub. Yes, and then I confirm an equation. Yes, exactly that equation. And let's, yeah, Copilot is telling me what you want to show. Yes, I want to show it. So let's see how it comes out. Yeah, there it is. So this is a second boundary condition. So this one, this one, this one. Perfect. Perfect. Now that we have two boundary conditions, meaning we have two equations and three unknowns, one of those unknowns is W, omega, angular velocity, which we need to find a value according to the maximum shear stress elastic theory of failure. Then one thing we could do is to find out the values for Z1 and Z2. So next, okay, we'll solve for C1. Actually, it would be nice to write it as an equation, as a formula, latex formula. C1 and C2, missing the C2. Yes, from the equations derived using the boundary conditions. Great. Let's write it down. So this is going to be pretty simple, actually. And I'm going to write the comments here solving for C1 and C2. Look at this. So Copilot suggesting, okay, solve this one and this one. Yes, these two boundary conditions, equations for C1 and C2, but I don't want solve, I want linear solve. This one here, yes. So I want to get them, and let me plot, let's say plot them to see how they come. Not just a plain value, just like this. So we have two values. So this is for C1 and this is for C2. Now we need to extract those values into the individual parameters. So I'm going to repeat it here. Yeah, I don't want this output in the report, so I could just eliminate this and say, well, now I know that C1 value equals to, I need to extract it according to that form from this first value, from the result. And then I'm going to extract the argument. This is C1, yes, and then C2 has to be, yeah, this argument here. Let me display them here. Yes, but I want to write here that is C1, actually R. C1 equal to this one thing, and then I know that it's coming with a lot of decimals, so I'm going to just constrain the decimals to 3 there. Expected member after that doesn't make sense. Maybe there's an error here I'm having in the button. But then if I put this display here, yes, let me see what's the error here. This should be fine actually. So let me see. Yeah, they came here. So we have the value of C1, value of C2. All of those, both values are in function of the angular velocity. It was expected. Now that we have these two values, what we could do is that substitute back into our equations for stress and strain, stress radial and circumferential stresses in here. So now that I have here, I could substitute these values, C1 and C2, in these two equations, and then I would have basically the final equation that I could use to evaluate at a certain radial distance or at any point in the disk along the radius, of course. And then I'm going to write down here substituting back to the, let's say this one, sigma r. Oh, sigma r, and like this, sigma theta equations. But as this is latex, I need to write down this and this one here. Equations. But it would be nice to have some numbering so we can keep track of these. Subs. Yes. And yes. See how it goes. So sigma equation, yes, that's correct. And sigma theta equation, yes, that is correct. And I want to display them. Yes, and yes. Perfect. So let's see how they come out. Well, let me again, well, I should have done it. So let me restrict this to 3 decimal positions. This one here and this one here. Yes, SP. And again, 3 decimal positions. Yes, there they are. Awesome. Now what else? So now that I have this equation, it comes to the point where I need to know what to do with this premise that I need to use the maximum stress criterion of elastic failure in this. So we have done in the previous examples that in these cases where we're dealing with a disk with a central hole, the maximum stresses are going to be presented or say developed in the here in the surface where the internal radius is. Yeah. So meaning that sigma r and sigma theta, so this both values are, or the maximum stress are going to be found there, even though if we take a look at sigma r in this internal radius is going to be 0, but then, you know, we're going to have sigma theta, which is going to be the maximum of everything. So we need to evaluate then that, or consider that the failure might happen in this area here, or in the vicinity of this periphery here, which means that that's the point I need to evaluate or analyze. So we could, let's say, find out what's the maximum angular velocity that this would allow under these conditions. So let's take a look at that. So let's come back down, 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 and say here that, again, let's write a little bit of comment that maximum stresses are found at, and then are equal to Ri. Then we can form the expression for the maximum shear stress. Oh my goodness, stress at this point. So let me write down the formula for the maximum shear stress, and that's going to be that basically tau. Yes, tau. It's going to be equal to the relation between stresses and stresses. Basically, it's going to be, in this case, for the two or bidimensional case, it's going to be equal to the relation that exists between, basically it's just like that actually, sigma, then here theta, minus, so circumferential stress minus the radial stress. I'm missing, yes, this is correct, and then I need to put the denominator here, which is 2, perfect. And then let me just print it out. Oh, something went wrong. I didn't close the equation. So this one here. For me, the expression. Oh. For Tresca, we're going to have that. Let's call it tau. Yeah, tau max. There it is, but well, Copilot is pretty smart in this case, but no, it's like this. Yes. Now, if I have those two, yeah, let me display this equation to see how they come. Tau max is this one here. Yes, I want to. Let's see how it comes. Look at this. Awesome. Yes, yes, and yes, perfect. Now let's substitute, or let's say that we need to compare this with the strength of the, let's say with the strength of the material. So let me write down here, comparing the maximum shear stress with the strength of the material strength. So in equation way would be that this maximum shear stress, basically, and I can write it kind of as we wrote it here, tau max, is going to be equal to, then that, actually it's going to be fraction of the strength of the material strength, divided by 2. Yes, something like this. Comparing the shear stress with the yield stress. Yeah, basically that's it. And yes, I want to form this equation, tau max equation, but this is going to be divided by 2. Yes. And let's see how it goes. So let me display at this point how it goes. And yeah, there we have it. This is what's corresponding to the maximum shear stress. This is what's corresponding to what I need to compare against the material strength of the steel in here. This is perfect. Now let's solve for omega. So we need to solve for omega. And solving for, again, the angular velocity. For this specific case, we're going to have that, and let me write the comment again, solving. Well, it's not critical speed, but for angular velocity. And yes, I need to solve from this Taumax equation, I called it. Let's call it that, then we are going to call that omega value. Just a second, I define omega W as one of my, nope. Doesn't matter because we have here omega value equals to solve these two equations, yes. And then I just want to know how much is this omega value. Let me see how it goes. Well, it's given me two answers. One seems to be negative, one is positive. I could have solved this by just forcing some certain of these symbolic variables to be only positive. Okay, but yeah, let's take just the first one. Yeah, let's take the first one here. So let me see if I have, what about if I just want to print the first one? Okay, one of the things that is not allowing me to do is that I still have some R here, sigma Y here. So I better substitute those in here. So, okay, sigma val. Yeah, let's substitute sigma. Yeah, and the R that I should substitute here, I don't know why I didn't do it before, but that's okay. So I need to substitute these two values, which are known, and then also the value for R. And now this is the internal radius here. And then I could, actually let's take the first value because the first seems to be the positive one. Yeah. Well, let's see. Why is, okay, my bad. Val. Yeah, there it is. So this is the value of the angular velocity, and let me display it better. Display. Yes, and then I'm also going to write that this is going to be in, let's say this is here, here, plus, what about if I put here radians per second? Yes, that's what I want. Oh, flow to string. Sorry about this, but I believe I need to write this one here. No, it's not allowing me, so I'm doing something. R this plus this. Just a second, let me figure out what's happening here. I believe that, let me see if Copilot helps me. Okay, yeah, I believe it was something about how I was presented the information here. No, it's not letting me. Too bad. Incomplete input. Just okay. Oh, I really would like to write down this here. This is strange. Just bear with me because this should be. What about if I write this? Okay, now. Right, sec. There it is. Now let's put some spacing here. There it is. So these are in radians per second. And well, let's transform it to, and then now presenting, finally, we'll present the angular velocity in RPMs. So to do that, so comments in here, starting transforming, transform in the to RPM. There it is. So yes, I need to have this RPM value. That's correct. And then I need to display it. Yes. Perfect. So let's see how it goes. And here it is. So here's the final answer. So that is 7,430 RPMs. Should I use more RPMs here? Yeah, it's okay. So this is the final answer. And we managed to do everything here with the help of Python. And one thing that I would like to do is to export this as my, to call it, a PDF maybe, so I can, if I want, I can turn it in. Okay, now I'm going to transform this into a report. So I have my virtual environment activated. I am in the right directory, so I will write the command Jupyter notebook convert, and then the name of the notebook, exercise 2 to solve, then interactive Python notebook. And then I want to convert that to a PDF with no input. Yes, so let's do it. Exercise, I believe it's okay. It's going to take a little bit. Let's wait for it. Right, so let's check it out. So let's open that PDF file recently created. So it's this one, and let me show you how it looks like. Here it is, so you can see it. So exercise to solve is the title, so that could be changed. So April 2, today. And yeah, we can work with this. I said that if we export this into LaTeX, then we can modify it as we wish. So perfect. So you see how equations are formed, and all what we are doing, all the comments appear there without the need of writing some. Well, we could have modified this a little bit, put some units. But now we have a pretty much working report that we could just fine tune and get the final report. So this is something you might use in some other courses that you are taking, or you would like to implement this. But this is a very convenient way to do it. I would export it to LaTeX and then modify it. So that would be the nice way to do it. Great, so I will stop now, and I might do another exercise about rotating thin disks, to a very interesting one, to find maybe the thickness of a disk, that complies with certain characteristics. And then from there, I believe we have all the tools or ingredients to solve any exercise that it's put in front of us. But thanks for being with me or staying with me until this moment, and I'll see you again in the next video or lecture.